Hey everyone, and welcome back to the Trending Tech Show. I'm Alex, and today we're diving deep into the world of database transactions, how they keep our data safe, prevent chaos when many users interact at once, and why they matter for every application, from your bank to your favorite online store. I'm joined as always by Sam, our resident database expert. Hey Sam, great to have you back on the show.
Thanks, Alex. Always excited to talk tech with you. And honestly, the way databases handle transactions is both fascinating and essential to so much of what we take for granted online.
Let's start right from the beginning. When people hear the word transaction, they might think about swiping a credit card or moving money between accounts. But in databases, what exactly is a transaction and why do they matter?
That's a great place to start, Alex. In the database world, a transaction is basically a sequence of operations, reads and writes, that we want to treat as a single, indivisible unit. The classic scenario is you want either everything in that group to succeed or nothing at all. Imagine transferring funds between two bank accounts. You want to make sure the money is deducted from one account and added to the other in the same operation. If something goes wrong halfway through, like the system crashes, you don't want the money to disappear or appear out of nowhere. That's where transactions come in.
So it's like an all or nothing deal. Either the whole transfer happens or none of it does.
Exactly. This all or nothing concept is what really makes transactions so valuable. It simplifies things for us developers, so we don't have to worry about what happens if a failure or crash happens halfway through, or if multiple users are trying to change the same data at the same time.
I've always heard about this ACID thing when it comes to transactions. Could you break down what ACID stands for and what each part really means?
ACID stands for Atomicity, Consistency, Isolation, and Durability. Let's take each one step by step. Atomicity means that all parts of a transaction must succeed together, or if any part fails, the whole thing is rolled back as though it never happened. Think of it like flipping a light switch. It's either on or off, not stuck in between. Consistency is about making sure the database always stays in a good state, where all the rules you care about are followed. If you have a rule that says two accounts must always total a specific amount, a transaction can't violate that rule. Isolation ensures that when multiple transactions are happening at the same time, they don't mess with each other's results. It should seem as though each transaction is running alone, even if, under the hood, they're happening concurrently. Durability promises that once a transaction is marked complete, its changes are saved, no matter what. If the power goes out, for example, your committed changes shouldn't just vanish.
Makes sense. And I love the light switch analogy for atomicity. But real life is messy. Systems crash, networks fail. Sometimes multiple users try to grab the last seat at a concert at the exact same second. How do transactions actually help with these sorts of failures or race conditions?
That's where transactions shine, honestly. In the wild, our systems are bombarded by all kinds of potential problems. Hardware might fail, a user's app might crash, you might lose connection halfway through a process, and, as you mentioned, several users might try to update the same data simultaneously. Transactions act like a safety net. If something goes wrong in the middle of a group of operations, a system crash or some error, the transaction is aborted, and the database undoes any work it did for that transaction, so you don't get half-finished or corrupted data. This lets you as a developer write code for the happy path and rely on the database to keep things from getting inconsistent beneath the surface.
So transactions are there to ensure that it's not possible to end up with an in-between state, even if something unexpected happens. But are all transactions the same? Or do different databases handle them differently, or provide weaker or stronger guarantees?
That's a great question. Not all transactions are created equal. Over time, different databases, especially as we moved into the NoSQL era and distributed systems, have made different trade-offs. The classic relational databases, like MySQL, PostgreSQL, or Oracle, were built around strong transactional guarantees, but many newer systems, especially the early NoSQL databases, sacrificed transactions entirely, or offered a weaker version, all to get better performance and easier horizontal scaling. The result is Some databases offer full transactions supporting the complete ACID properties, while others only offer atomic operations on a single piece of data, or something in between. So, when someone says their system is ACID compliant, it's worth digging into the details, because those guarantees can vary.
That sounds like it can get confusing pretty quickly. And you mentioned single object operations. What's the difference between a transaction on a single object and a transaction that works on multiple objects?
Let me explain using an analogy. A single object transaction is like editing a single paragraph in a shared Google Doc. You lock just that paragraph, or maybe you rely on Google to make sure two people don't write over each other's words at the same instant. It's simpler. If you can keep all your updates within one object, it's easier to make them safe and atomic. But life and data are rarely that simple. Multi-object transactions involve making coordinated changes across multiple documents, rows, or items. Think about an email system. When a new email comes in, you might need to add the message to a folder and increment the unread count somewhere else. You really want both updates to happen together. Without a real multi-object transaction, it's possible for the email to appear, but not the counter to update, or vice versa. So, single-object transactions are simpler, faster, and easier for databases to provide. But for many real-world applications, you need multi-object transactions, at least some of the time, to keep related pieces of data consistent.
Do most modern databases provide multi-object transactions? And is there a downside to using them?
Some relational databases provide robust support for multi-object transactions. Every statement between a begin and commit command is grouped as a transaction. Many NoSQL or newer distributed databases historically did not. But things are changing there too. The main downside is performance, especially in distributed systems. Coordinating multiple pieces of data, possibly spread across different servers, adds a lot of overhead and complexity. For large-scale, high-traffic applications, this coordination can become a bottleneck. That's why you'll see debates. Some engineers argue that we should only use multi-object transactions when absolutely necessary, relying more on single-object atomic operations to keep systems fast and scalable.
So, it's a balancing act. Use transactions for the right scenarios, but be mindful of performance implications. Let's get into some of the bad things that can happen when isolation isn't strong enough. Can you walk us through the weak isolation anomalies we hear about, like dirty reads, dirty writes, and lost updates? Maybe with some real-world examples.
Absolutely. When we loosen isolation for performance, certain quirks can pop up. Dirty read. Imagine your coworker is updating a shared spreadsheet cell, but they haven't hit save yet. You look at the new value, but then your coworker decides to undo the change. Now you've seen a value that never actually existed officially. A dirty read. In databases, this can cause big problems if you base another calculation off that dangling value. Dirty write. This happens if someone writes a value but hasn't confirmed their changes, has not committed, and then someone else writes on top of that unfinished work. If the first person decides to cancel their changes, now the second person's work is sitting atop an invalid base, leading to confusion or data corruption. Lost update. Say you and I are both updating our company's website homepage at once. We both download the page, make separate edits, and upload our versions. If yours is saved last, all my changes get wiped out. My update is lost. Databases with weak isolation, like the default read committed, typically prevent dirty reads and dirty writes, but not lost updates unless you add extra safeguards.
And are there ways we can prevent those, or at least minimize the risks?
For sure, databases offer different isolation levels to strike a balance between protecting against these anomalies and allowing more concurrency for better performance. At the basic level, read committed protects against dirty reads and dirty writes, but preventing lost updates often requires using atomic operations, explicit locks, or higher isolation levels. For things like lost updates, the safest way is using atomic database operations, like increment, compare and set operations, or explicit row-level locking in your code when you do read, modify, write cycles. Some databases can even automatically detect lost updates and abort one of the conflicting transactions, which helps a lot.
Terms like repeatable read, snapshot isolation, and even serializable thrown around. How do these isolation levels fit together, and what's the difference between them?
Great question. Think of isolation levels as layers of protection, each one trading off between safety and performance. Read committed. The baseline prevents dirty reads and dirty writes. You only see finished work. Repeatable read, snapshot, isolation. This is a step up. These make sure that when you start a transaction, you see the database as it looked at that moment, like a photo snapshot that doesn't change, even if other users make changes after you started. This prevents non-repeatable reads, where rereading the same data in your transaction could have changed. Serializable. This is the gold standard. Your transaction acts as if it's the only one running, period. The final effect is the same as if everyone had taken a number and waited in line. No overlap at all. But higher isolation levels can impact performance, especially when lots of transactions compete for the same data. So, snapshot isolation, often called repeatable read in some databases, has become super popular, especially for long-running analytics queries, because it doesn't block writers and readers from each other.
I keep hearing about this snapshot isolation and multi-version concurrency control, MVCC. Can you explain how this works and why it's so powerful?
Sure thing. MVCC is a clever system where, instead of locking data for every read or write, the database keeps multiple versions of each piece of data. When you start a transaction, you get a snapshot of the world at that point. If someone else changes that data while you're working, those changes create a new version, but your transaction still sees things as they were when you started. It's like being in a library where, when you check out a book, you get the edition that existed when you arrived. Even if a new edition comes out, your reading experience isn't affected until you come back later. This allows writers and readers to work concurrently without bumping into each other, which is great for performance and usability, especially for systems with lots of reads.
That's really clear. But are there any pitfalls? Are there cases where even snapshot isolation isn't enough?
There are. Two important anomalies still slip through: write skew and phantoms. Write skew. This happens when two transactions both perform a check and see that some rule is satisfied, so both proceed. But because they're running concurrently and make independent changes, the combined effect breaks the rule. Remember the hospital example. If both doctors check and see that the other is on call, and both decide to go off call at the same time, suddenly, no one is left on call. Phantom reads. This occurs when, in the course of a transaction, new data pops into or out of your result set because of another concurrent transaction. For instance, if you query all bookings for a meeting room to make sure it's free, but before you confirm your own booking, someone else sneaks in and grabs the slot, you might end up double booking. These issues generally only go away if you use the highest isolation, serializable, or manage things with explicit locking or special database constructs. That's the million-dollar question.
That sounds like a real headache, especially if you only find out about these subtle bugs after your app is live. So, serializable isolation is the answer. But is it always practical?
In an ideal world, we'd use serializable isolation everywhere and sleep well at night. But it typically adds overhead, slower performance, more blocking or failed transactions, because the database has to coordinate things so tightly. Classic ways of getting serializability include executing transactions one at a time on a single thread, literally serial execution. Super simple, but it doesn't scale. Two-phase locking, 2PL. This mechanism tracks locks on data so that no concurrent abnormalities can sneak through, but it comes at the cost of performance and can result in deadlocks, a situation where two transactions are each waiting for the other to let go. Serializable snapshot isolation, SSI. This is a newer, optimistic technique. It lets transactions proceed in parallel, but checks at the end to see if any dangerous patterns occurred. If so, it aborts one and makes you retry. SSI is especially promising as it manages to combine the safety of serializable isolation with performance close to snapshot isolation, especially in databases like PostgreSQL and some distributed systems.
Optimistic concurrency control? That's not a phrase you hear every day. How is that different from the kind of lock-based approaches you mentioned?
Good catch. Optimistic concurrency control, as the name implies, is based on the hope that conflicts will be rare. Rather than blocking transactions from running if there might be a conflict, everyone goes ahead and does their work. At commit time, the database checks to see if anyone has stepped on each other's toes. If so, one transaction is rolled back and has to be retried. Lock-based, pessimistic approaches, like 2PL, assume the worst. If there's any chance of a problem, transactions wait for locks before doing their work. This avoids conflicts, but it also means you might have lots of transactions waiting around, slowing things down. Optimistic methods work great when most transactions don't overlap or conflict. Think of a highway where cars usually flow freely instead of a series of traffic lights stopping every intersection. But if there's too much congestion, lots of transactions touching the same data, optimistic control can lead to many retries, which hurts performance.
Are there any new technologies or developments in this space? Maybe systems that adapt their approach based on what's happening at runtime?
There's ongoing research into adaptive transaction systems. For example, newer frameworks can monitor whether transactions are running into conflicts frequently and can automatically adjust the isolation level or concurrency control mechanisms accordingly, dialing up strictness when needed, but relaxing it when things are running smoothly. Some database engines even use machine learning or dynamic algorithms to predict contention and balance performance against correctness needs.
Really cool stuff, Sam. Let's bring this home for our listeners. If you're building an app or service and have to choose how to handle transactions, where should you start? What are some best practices?
First, understand your application's needs. If you're working with mostly independent items, think a key value store where users only touch their own records. Lightweight single-object atomic operations may be all you need, and they're the simplest and fastest. If you need to keep multiple pieces of data in sync, like inventory and orders or related tables, embrace multi-object transactions and the strongest isolation level you can, at least for operations where consistency is critical. In high concurrency environments where performance and throughput are crucial, and you know what anomalies you can tolerate, consider snapshot isolation, or even tuned weaker levels, but be very careful about the risk of anomalies like write skew or lost updates. Always handle transaction failures gracefully. If a transaction aborts, be ready to retry, but do so wisely. Use exponential backoff and don't hammer your system in the process. For distributed or cloud-scale databases, understand how your system handles transactions. Read the fine print on what ACID means for your chosen platform.
We'll be back next week with more deep dives on the tech that shapes our world. Until next time, keep learning and keep building.